Forward kinematics, just a recap. So based on the link length and joint angles, we will be calculating the position of the end effector, that is forward kinematics, and in inverse kinematics, based on the given position, so we will be solving for the joint angles. So that is the inverse kinematics. Next topic is the differential motion. So which we will have a quick recap. I think I informed the other student last week. So this is the important one which we discussed. So XB. So this is the those who are absent for the previous classes. Just remember, this is the position in X and this is the position in Y. So where L1 is the link length of link 1 and L2 is of link 2, and this is for a 2D planar robot. So consider we have a planar robot. So we have one revolute joint over here. So and you have a robot arm. So you have this end effector, so which is your end effector. So this is L1, this is L1, and this is L2. So L1, this is L2. So L1 is your link length of link 1, L2 is link length of link L2. So both are revolute joint, and we have angle theta 1, which is representing the joint angle of link 1, and this is the theta 2, which is the joint angle of link 2. So our intention is we have to find out what is my end effector position. So this is my XB, x comma y. So this is x comma y. So this is x which was provided over here. So consider this is x-axis, which is in the horizontal direction is your x-axis, and the vertical is your y-axis, which is a planar robot we are talking about. We are not talking about the spatial robot, we are talking about the planar robot. So x, y. So we resolve the link L1 into two components. The horizontal component is cos theta, and the vertical component is sine theta. So if you are interested in finding out what is this position, then it is given by L1 cos theta 1, which is your horizontal distance from here to here, and the vertical distance is L1 sine theta 1. So this is L1 sine theta 1. So this first term will tell you what is my position over here, what is the position over here. But our interest is we have to find out what is my end effector position, XB and YB. So for that, this is the notation which we solve using forward kinematics. L2 cos theta 1 plus theta 2. So we have to add it up these terms, because this theta 2 is separately from here to here, it is L2 cos theta 2 and L2 sin theta 2, but with respect to the world frame, so this is provided by L2 cos of theta 1 plus theta 2. So which is which combines both the theta 1 and theta 2 values, and the vertical point y. So this is your horizontal component x, and the vertical one is y. So this vertical y is provided by L1 sin theta 1 plus L2 sin theta 1 plus theta 2. So this is solved. This values you can get using the forward kinematics. So this is using forward kinematics. So as I told you, so in forward kinematics, so based on the provided link length and angular values, joint angles, theta 1, theta 2 are joint angles. These everything will be known. and from that we can find out what is my position. So this is the position value. So this position x and y, we can solve it using forward kinematics. So this is a simple notation which is specifically for a 2 DOF planar robot, considering both the joints are revolute joints. So this one is revolute joint theta 1 and this one is revolute joint theta 2. So this is the positional values which was solved using forward kinematics. So in the differential motion, so our interest is more about not only solving for the forward kinematics. We have to find out how the robot moves from one point to another point. So that is what talks about this differential motion. So we have to differentiate this values x and y with respect to time. So because velocity is nothing but change in displacement with respect to time. So that is what we are going to do over here. So we are going to differentiate dxp. So L1 cos theta 1 will be when you try to differentiate it. So this becomes the cos theta will become sin theta. So minus cos theta will become minus sin theta. So that is minus L1 sin theta 1 d theta 1. So d theta 1 or theta dot. So both can be used. And when you differentiate L2 cos theta 1 plus theta 2, and this is the differential term. So minus L2 sin theta 1 plus theta 2 multiplied by d theta 1 plus d theta 2, or theta 1 dot. So it can also be given as theta 1 dot. So this dot term is also the differential term which you can find out in most of the textbooks. So d theta 1 or theta 1 dot plus d theta 2 or theta 2 dot. So similarly, when you try to differentiate the y term, so L1 sin theta 1, when you try to differentiate it, it's L1 cos theta 1 d theta 1 plus so L2 cos theta 1 plus theta 2 into d theta 1 dot plus theta 2 dot. So this is the term we get upon that differentiation. So we separate this term. So this d theta 1 d theta 2 separately. So and this is the final point we get using the relation. The differential motion of B is equal to this matrix is your Jacobian matrix, and this is your joint differential motions. So the Jacobian, in the simpler terms, this Jacobian is the major component, so which defines how the joint velocities have to move based on the end effector velocity. So these terms will tell you what is my end effector velocity. So this dxb and dyb will tell out what is my end effector velocity, how this end effector is moving. So based on that, the joint velocities also have to move relatively, and that factor is provided by the Jacobian. So this is a very basic concept of Jacobian. So this is the very basic thing before moving into the dynamics part. So we have a few rotational matrices similar to the transformation matrix, which was seen in the forward and inverse kinematics. So the differential motions is provided by the del x. When we are trying to rotate my robot end effector about an x-axis, and this is the matrix we will be solving, and the final matrix is your differential operator. So this is the final differential operator matrix which will be used for solving the problems. So the few problems uh, I think the last class I told one student also. So we have to combine all these things. The solving ones we will see directly in the offline classes. Most of the topics will be covering in the online. So this is the relation how to use the differential operator. So d is nothing but your end effector velocity. So this is the very important relation. So d is your end effector velocity, j is your Jacobian, and d theta is your joint velocities. So Jacobian is used to relate your joint motions with the end effector motion. So these are all the various components in your end effector velocities: dx, dy, dz, and del x, del y, del z. So these are all the six terms which will be used in the D matrix, which tells you these three are linear velocities, and these three are angular velocities. So we will substitute everything in the differential operator, and we will find out what is my change, a differential change. And with this, we will find out what is my new position. So initially, the robot will be in a position one, and it has to be moved when you provide some differential changes, differential motions, either in the joint velocities or in the end effector velocities. There will be a change in your position of your robotic arm. So that is this is the steps and procedures to solve it. And we have one problem over here. So we will see that also. And this is the meaning of the Jacobian. It is a representation of geometry of elements of a mechanism in time. So it is time related. It relates the velocities of individual joints, that is the joint velocities, to the differential motion or velocities of the end effector. So this is the important one. You can check this in the PPT that was provided in the Google Classroom. So it is time related, and it tells you how your robot arm will move. When the end effector velocity is provided, the joint motions will also move relative to the end effector velocity, and that is provided by the Jacobian. So we have y as a function of x, and based on the partial differentiation, so we will calculate all the things. This is y, you can take it as your end effector linear velocities and angular velocities, and x is your joint velocities. So when you try to do a partial differentiation, so with respect to x1, x2, so on and on for all the joints. Suppose if it is a 2 dyf, it will end up with y1 and y2. If it is a 6 dyf, it will move along to the 6 rows and 6 columns. So upon the partial differentiation, we finally get this linear components. So these three are linear velocities. So this is the linear velocities, and this is your angular velocities. And these three are angular velocities. So Jacobian talks about only the velocity terms, and this is the Jacobian. So this is a matrix, and d theta 1, d theta 2. So d theta 1, theta 2, theta 3, 4, 5, and 6 represent your joint velocities. So joint velocities in the sense the individual joint movements. So suppose if you provide d theta 1 of some values in terms of a radian, so only that will move with respect to time, how this joint will move from time t is equal to 0 to t is equal to 1. So this is the velocity terms which will be provided in your problems, and this is the important relation: d is equal to j into d theta. So in some of the problems that we will be solving, d theta will be provided, and Jacobian will also be provided, and we have to find out what is my velocities. In most of the real-time problems, you may also find out, you may also be provided with the end effector velocities. So this will be provided, and we have to find out what is the corresponding joint velocities, and for that we have to take inverse. So we have to take an inverse if d is provided, and if we have to find out what is my d theta. So in most of the problems, this is the uh, issue that will be there, and we have to take a j inverse. So we have to take a j inverse and d theta. So two scenarios are also possible. If you are provided with the joint velocities, so it is very easy to calculate your end effector velocity. And if you are provided with the end of if you are provided with your end effector velocities and solving for this joint velocities, you have to take inverse. So these are all the two relations which will help in solving for the Jacobian. So this is one problem. If you have a notebook also, you can try to solve it. So the Jacobian of a robot at a particular time. So in this differential motion, it is more about time related. So at a particular instant of a time, this is the Jacobian, and this everything will be provided. The Jacobian values, everything will be provided at an undergraduate level, and in the higher levels, you have to solve for this one. Then this is the there are some relations are there, so that is not required at an undergraduate level for determining this Jacobian matrix. In most of the problems, the Jacobian will be provided already, and we are also provided with the joint velocities. So everything in terms of a radian. So 0, 0.1, 0, minus 0.1, 0.05, and 0.03. So everything are joint velocities which are provided in radians. It is not in degree, it is provided in radians. So the Jacobian of a robot at a particular time is given. We have to calculate the linear and angular motions of the robot hand frame for the given differential motions. So you are provided with the joint velocities and Jacobian. So you have to solve for the interfector velocities. So you can take your notes and you can try to use this relation and try to solve this problem. So I need to know what is the answer. So everything is matrix multiplication. So this is the relation we have. So relation we have, we are provided with the Jacobian, and we are provided with the joint velocities, and we have to find out what is my end effector velocities. So can you solve it?
Yes, sir.
Yeah. Anyone solved?
So 0.1 minus 0.1 0.03.
Can check the answer.
Yes, sir.
0, 1.5, 0.15.
0.15 again.
Yeah, you can verify the answer over here. So this is the dx, dy, and dz, and this is the del x, del y, and del z. So you can use the calculator, online calculator. So like if it is 1.5 radian, so if it is 1.5 radian, if you provide 1. I mean like if you provide theta 1, this is a theta 1 differential value. This is a theta 2 dot, theta 2 dot, it is 0.1, and so on and on. So these are all the final linear velocities and angular velocities. So if it is a 0.1, you can verify in your calculator. So zero point 0.1 radian is 5 degree. So zero point 0.1 is provided in radian, it is 5 degree. So if theta 2 was moved at an instant of time of 5 degree, and theta 3, this is theta 4, theta 5, and theta 6. So this is the changes you find in your linear and angular velocities at the end effector. So these are all the joint level changes, and this is at the robotic end effector changes. So similarly, we have a few more problems. A frame as so frame is nothing but as I told in the first unit, a frame is nothing but your homogeneous transformation matrix, so which will tell you what is my position and orientation. So when you look at here, so these three are the position. So these three are the positional terms, and these 3 cross 3 is your rotational or the orientations. So rotation or orientation. So this is nx, ny, nz, ox, oy, oz, and ax, ay, az. So these are all things discussed in the forward kinematics. So these three represents your orientation of your robot end effector, and these three terms will tell you 3, 7, and 8 will tell you what is my position. So position in the sense it is in x, px, this is py, and this is pz. So on a 3D space, so 3, 7, 8 is my positional vector values in x, y, and z. And the initial the robot in this problem, the frame B is translated by differential amount of translation of 0.02, 0.04, and zero 0.03 units. Find its new location and orientation. This is the initial position and orientation of your robotic arm. So when we provide some differential movements, we have to find out what is my new position and orientation. So in this problem, so this is the initial this is the initial differential formula, so which you can see in the previous slides. So this is the only translation. So in the vector translation, I think you can see, you might have seen that. So this is the identity matrix. In case of a pure translation, there is no change in the rotational or in the orientation, and there is only change in your position. So we are providing only some positional changes, and that will be multiplied by this old matrix, and this is the final value. So when you look at here, when we provide some differential motion, differential movements, so only a translation. So three components of transmissions are there. One is pure translation, pure rotation, and a combination of translation and rotation. So which you might have seen in the Robo Analyzer software, and you can see that based on the pure translation, we can find out only the changes in your positional values, and there's no change in your orientation. When we provide some rotations, so that then only you can see the changes in your orientations. So and it is also one more problem. So the hand frame of a 5D wave robot. So you have a 5D wave robot. Its instantaneous and numerical Jacobian is provided. So this is the Jacobian of a 5D wave robot, and a set of differential motions are given. So this is the set of differential motions. So this is a set of differential motions which was provided, and we have to find out the new location of the hand after the differential motion. So to find out the new location, this is the initial location. So this a T6 will tell you this. You have to split it into the position. So this is the position, and this is the orientation. This is the position, and this is your orientation. So some of you are not aware of this. Okay. So just a recap so that you can understand this concept, what I was trying to tell you. So you have this world frame and a base frame. So consider this robotic arm. You have this world frame and a base frame. So this is your end effector. This is your end effector frame, and this is your tool frame. This is your tool frame. So when you look at here, we can provide. You can see over here some few transformations are possible. One is the translation, and the next one is your rotation. So translation can be along x, y, and z, and rotation can be along x, y, and z. So x is provided by this red color one. Y axis is your provided by green color, and z axis is blue color. So you can remember this clearly. So now if I want to move this tool frame to here, so what I can do, if I want to move this tool frame from here to here, என்ன பண்ணலாம்?
Rotation about X.
Rotation about x. Oh, we will try that. So rotation about x. Rotation about xங்கிறப்போ x frame மட்டும் கான்ஸ்டன்டா இருக்கும். The remaining will get rotated. You can see over here. X frame மட்டும் கான்ஸ்டன்டா இருக்கும். The remaining two frames will get moved. The remaining two will get moved. You can slightly move this robot. Okay, try to move this, and then we will try to rotation along x. Rotation along x. So when you are trying to move with respect to the tool frame, so you can see a change in your joint angles based on the velocity. Suppose if I move along y-axis, this is your linear velocities. When you are provide some linear velocities, that is change with respect to time, you can see a differential change in the joint angles. So independent joint angles you can see over here. When you try to move the end effector, you can see different changes, and those things is related by the Jacobian. So when you look at here, this is the initial position. Suppose you take this term position. So 360, 113, 599. This is your position, which will be determined based on the transformation matrix. And the next three is your orientation. Next three is your orientation. And 532 will similarly over here. 532 will tell you about your position. And these six terms will tell about the orientation. Initially, the hand frame of a 5D wave robot. This is the initial matrix T6, and this is my robot position. Its Jacobian is also provided, and we are also providing some differential motion in joint level. So joint level in the sense we are not moving this end effector movements. We are providing some theta one. So now ultimately you can see that there is a change in your position. When you provide some joint movements, we can provide a change. You can see a change in your positions. Similar to this, we are providing some differential movement of point 0.1 in the theta 1, minus point 0.1 in theta 2. So this theta 1, d theta 1 is your joint 1 velocity. It is not joint angle, it is joint velocity, theta 1 dot. So this we are providing some joint velocities, and Jacobian is also provided. And initial, this is the initial matrix. Now what they are asking us to find out is the new location of hand after the differential motion. So this is d theta, which was provided. This is a d theta. This is a d theta, and Jacobian was also provided. And based on these two, we can find out what is my d. It's nothing but your linear velocity and the angular velocity of your end effector. So we have these two values given in the problem statement. So from that we can find out what is my d. So d is nothing but it is a combination of d and alpha. So which is your joint velocities in xyz and angular velocities in xyz. So we have to substitute everything in the differential operator, and we have to add it up, the differential operator, with the old frame. So when you try to do this, we can find out what is my new location. So this is what being provided. So we will be solving for d. We will be getting all these linear and angular velocities. We will be substituting everything in the differential operator. This is the relation which was given in the formula in the previous slides. So based on that, we can find out what is my differential motion. So what is my differential motion? So this is my final differential motion. When we try to add up this differential motion with respect to the old frame, we can get my new frame. So when you see here, this is my position and orientation of my end effector at the initial initial time. So this is the initial time. This is my position and orientation of my end effector. And upon the differential motions that has been carried out, and this is my final position and end of position and orientation of my end effector. So this is how my robotic end effector has been moved based on the differential motions provided at the joint level. So when you see over here, 532 was my initial position in px, py, and pz. Now upon the differential motion that was carried out, so we get my position as 5.1, 2.85, and 2.1. This is my new position and position, and this is the orientation. So the robotic end effector have been moved based on the joint motions that are being provided. So this is the standard steps and procedures that are followed in calculating using the Jacobian. So next we will move to the important topic of dynamics. In your syllabus point of view, mostly they might have started with the dynamics part, and that is the reason I just starting at the end, the dynamics part. So in the previous chapters, we studied the kinematics of position, the differential motion. So the kinematics of position is you can get it from forward kinematics and inverse kinematics, and differential motion, which was we have seen in the previous one. So we look at the dynamics. So you can take down the notes uh, in kinematics. So we study about the relative motion between various parts of a machine or links without considering the forces. So that is the main important term. Without considering the forces, we will be studying about the relative motion. But in dynamics, you can write it down. It is the study of forces and torque causing that motion. You can note it down. So dynamics is the study of forces and torques causing its motion. So kinematics law, it is more about study of relative motion between various links. without considering the forces acting upon it. And in dynamics, it is the study of forces and torque causing its motion. So this is mainly based on the Newton's formula. So everyone is aware of force is equal to mass into acceleration. That is the base formula. So based on which we will apply this to a multi-body components like robotic arm. So where many links are getting connected, and the movement, suppose you consider link 1, link 2, and link 3. The movement of link 3 will affect link 1, and movement of link 2 will affect link 1, and movement of link 3 will affect link 2. So it is a multi-body system, and the relative motion of one component will relate or affect the other component. So this basic formula we will elaborate and apply into multi-body dynamics. So the horizontal force or the translation component is provided by F is equal to m into A, and the rotational component T is equal to I into alpha. So where I is your moment of inertia and alpha is your angular acceleration. These are the basic formulas. And force, you can mostly use it for the translation movements. We solve it for the force, and for the rotational one we solve the torque. In simpler terms, for a prismatic joint movements, we will be calculating this force component, and for the rotational component, that is your revolute joints and other things, we will be solving for the required torques to move the or to rotate the links. So in our robotic arm, so mostly the joints are revolute joints, and we will talk about how to arrive at this torque, suitable torque for the robotic arm. So that is the key aspect. Before designing a robotic arm, so we should be aware of the selection of an actuator. Actuator is in our case is nothing but your electrical actuator, nothing but your servo motor. So the selection of a servo motor is a very important aspect. So when you look at here, this is the first joint. So I think everyone is aware of. You might have used the Robot DK or Robot Studio or the actual real robot. When you look at here, so this is your first joint, and this is your fifth joint. This is your fifth joint. Look at here. This is your fifth joint, and this is your first joint. Is the actuation is based on the electrical actuator. The movement of this here also you have a revolute joint, and the degrees of freedom is 1, and this movement, I think everyone is now clear on how this joint 1 and joint 6 are moving. Can you tell me whether you are going to select same actuator or same motor for all the two joints theta 1 and theta 5? ரெண்டுத்துக்கும் ஒரே மோட்டார் தான் செலக்ட் பண்ணியிருப்பாங்களா?
No, sir.
எதனால? ஒய்?
Sir, first jointல வந்து ஆல்மோஸ்ட் மோஸ்ட் ஆஃப் எல்லா எல்லா லிங்க்ஸும் மூவ் ஆகுது,
ம்
அதாவது மூவ் பண்ணணும்.
ம்
லாஸ்ட் ஜாயிண்ட்ல வந்து நம்ம எண்ட் எஃபெக்டர் மட்டும்தான் இருக்கு. ஸோ
end
அங்க
effect.
வந்து
Okay.
ஒரு லிங்க் பிளஸ் ஒரு எண்ட் எஃபெக்டர்.
Since everyone are mechanical, a simpler concept is your a cantilever. Suppose you consider a cantilever beam. Assume this is your cantilever beam from joint 5. Assume this is your cantilever beam. This is the one end fixed and other end is free. So you have a load that is being applied over here, and this distance, consider from here to here, you take a certain distance. considered as L1. L1, you take, for example, you take it as L1 is your link length or the distance, and this is where your end effector is being placed, and you have a UVL load. So the link 5 has its own mass, and end effector have a different mass, and you have a UDL and a UVL. So from here to here it is UDL, and here to here the UDL, and when you look at from here from the joint 5, it is a UVL, uniformly varying load, that is being applied considering the self weight of the links, and the motors. You have a motor over here, and you are carrying some end effector payload, and everything will be considered. And finally we will find out the torque that is being required. This is L1. You consider this is L1, and you will get for example a torque of 2 newton meter. For example, you when you try to solve, you will find out here the torque required is 2 newton meter. So for this 2 newton meter, you have to select a suitable servo motor for overcoming this torque. So this is a torque for the opposing torque. You have to select your suitable servo motor. Suppose you take you buy a 2.5 newton meter torque motor for this joint 5. Similarly, when you try to apply the same concept to theta 1, similarly when you try to apply the same concept to theta 1, then you have to consider the whole link length, and this link L, L1, L2, L3, L4, L5, and all the other things. And you have some motors over here. Suppose if you consider this motor, if you here in this joint 5, if you have a 2 newton 2.5 newton meter 2 newton meter is your torque that is being generated for joint 3, whether you will get same torque of 2 newton meter or different torque, you will get it like 5 newton meter. So based on the simpler calculation is your distance for simpler calculation, but this is not the right procedure. I will tell you that procedure. Here you have from here to here, you have self weight of this link, this link, this link, this link, and here you in joint 4 you have a motor. So you have a motor over here, that motor weight will also be considered. Joint 5, this motor will also will be considered. Joint 6 also you have some motor, and you have the end effector, that weight is also considered. From here to here you will get for example a final torque of 5 newton meter, and this motor selection, the same thing you have to apply over here, and you have to select a suitable actuator to overcome this torque. So suppose you consider it as a 5.5 newton meter torque servo motor. Similarly, we'll applying the same criteria to the joint 1. So the joint 1 has to carry the entire robotic arm, and it has to move or overcome the torque that is being generated, considering all the link lengths. You have to consider link L1, L2, L3, L4, L5. Self weight also you have to consider. All the robotic links are rigid links, so you will have a very high load, and also a payload capacity. Also, the robot will vary, and that payload also has to be considered. And the gravity components will also be considered. Inertial components will be considered. Coriolis component will be considered, and centrifugal components will be considered. So these are all the various criteria that will be considered while calculating the torque for each and every joints. So that is where this dynamics is the very major role. So in this chapter, you will derive for a 2D way of robot arm how we are going to select a suitable torque. So that is what this unit is all about. So to accelerate robot joints, it is necessary to have actuators capable of exerting large enough forces and torque. So for overcoming the forces and torque then that is generated by the links, you need to have a suitable actuator. So that is where this equations will come into picture. So the dynamic equations will come into picture, and from the dynamic equations, so we will be calculating, or you will be finding the equation of motion, and from the equation of motion, so we will be calculating the forces and torque. So there are two ways to understand this or to derive this dynamic equation and solve it. One is Newtonian mechanics, and another one is Lagrangian mechanics. So first one is Newton mechanics, and another one is Lagrangian mechanics. So all are mechanical, so you will be aware of the mechanical terms. So Newton mechanics is mostly used in real world applications, but it is restricted to a lower DOF, and for the higher DOF, it is difficult to solve the Newton mechanics. And in our syllabus, we are going to talk more about the Lagrangian mechanics. Where Lagrangian mechanics is about the energy terms. So based on the energy terms, we will be calculating and deriving the equation of motion, and from there we will be solving for the forces and torques. So since the joints are revolute joints, so we will be calculating the torques at each joints. So in Lagrangian mechanics, there are two important terminologies are there. One is potential energy, another one is kinetic energy. So Lagrangian mechanics is based on the differentiation of a system's energy term with respect to system's variable and time. So it is a differentiation of a system's energy term. So energy term is nothing but kinetic energy and potential energy with respect to the system variables and the time. System variables here is your theta. System variables is nothing but your theta, L, M. So M is mass, L is link, theta is angles. So some of the variables in derivation you will see a few more things. So it is based on the differentiation of energy terms, that is kinetic energy and potential energy, with respect to the system variables and the time. So Lagrangian mechanics is based on this relation L is equal to K minus P. It is kinetic energy minus potential energy of the system. So for each and every links, we have to find out the suitable kinetic energy and suitable potential energy, and from that we can solve for this Lagrangian. You can note down this relation, so which is helpful for solving this torque formulation. So force is mostly for the prismatic joints, and T is mostly for the revolute joints. It is not dou by dt, it is d by dt. So there is one change, you can note it down. Torque Ti, I varies from 1 to n, where n is number of links. If it is 2 DOF, we will be solving T1 and T2. If it is 6 DOF, we have to solve for T1, T2, T3, T4, T5, and T6, where T represents the torque that is being required. D T is equal to d by dt, that is d by dt. So it's a time derivative of the partial derivative dou L by dou theta I dot. So theta I dot. So you can see over here it is theta I dot. Theta is your joint angle. Theta dot is your joint velocity. Theta double dot is your joint acceleration. So these are all the terms that you will see in the dynamics relations. Theta is your joint angles. Theta dot is your joint velocity. Theta double dot is your joint acceleration. So theta dot is nothing but theta 1 minus theta 2. Suppose you try to move say, first joint from 30 degree to 60 degree. You take it 30 degree to 60 degree. So initial position is theta 1 30. Final is theta 2 is equal to 60. So theta 1 theta 2 divided by t. So we have to differentiate this. So which is change in position with respect to time, angular position with respect to time. That is theta dot, that is your joint velocity, and theta double dot is your joint acceleration, that is change in velocity with respect to time. So this is a theta dot minus dou L by dou theta I. So I varies from 1 to n, where n is the number of joints. So this is the formula we have to solve it, the dynamics. So before going into that, small derivation to find out whether for a one DOF system, whether the Newton mechanics and the Lagrangian mechanics, when you try to solve it, we'll be getting a same answer or not. We will see in this one. So it is a simple spring mass system. So where M is a mass and K is the stiffness of the spring. So we provide a force. It is similar to this. In this you might have solved in your mechanical. So we have M over here, and we provide some force over here. This both are same. This one and this one are same. So there is some initial displacement x, which is being provided, and this is M and this is K, and this is the fixed one. Both are same. So what you might have solved in your vibration, both are same here. So we will try to find out whether we are getting the same relation using Newton mechanics and Lagrangian mechanics for the simple 1 DOF system. So it is a 1 DOF system of a spring mass system. So first we will see by the Newtonian approach. So this is the free body diagram which we have, where force is provided, and this is the reactive force, and this is the gravity, and this is the reaction force. So by the Newton mechanics, so we provide this formula F minus kx, the horizontal component. F minus kx is equal to max. So substitute over here in this approach. F minus kx is equal to m into ax, where a is your acceleration. So F is equal to max plus kx. So this is your final relation to solve for the force required. The same concept we will try to apply using the Lagrangian. This is the Newtonian approach. The next one is your Lagrangian approach. So Lagrangian approach, we take this, since we are talking about the kinetic energy. So this formula I think everyone is aware of. K is equal to half mv square. This is your kinetic energy formula. So where v is the velocity term. Velocity is nothing but change in displacement with respect to time, which is provided by x dot. So this is the kinetic energy term, and this is the potential energy term. Potential energy for a spring mass system is nothing but your strain energy, and this is provided by half kx square. We have this relation L is equal to K minus P, where L is Lagrangian, K is kinetic energy, and P is potential energy. You substitute these values over here. This is half mkx square here, and of kx square over here. So we get this one, and we have to do the partial derivative dou L by dou x dot. So this is L value. This term is your L value. It's a L value. So you perform a partial differentiation over here, dou L by dou x dot. So we get it 2 half into 2 into mx dot. So 2 and 2 get cancelled. We get mx dot, and after the partial differentiation you have to perform the differentiation time derivative one, and we get mx double dot, and the next term is dou L by dou x, which is provided by minus kx. So this formula, this d by dt of dou L by dou x dot minus dou L by dou x, so which you will get over here. So this is by for the force, since we are talking about the prismatic moments. So we take this formula now, d by dt of dou L by dou x dot minus dou L by dou x. So that is what we are solving over here, dou L by dou x dot, dou L by dou x dot we have solved. Next d by dt of dou L by dou x dot. So that is mx double dot, and dou L by dou x, that we will get it. So final force relation is F is equal to mx double dot plus kx. So this is similar to the one we solved using the Newtonian mechanics. F is equal to max plus kx. So A is provided by the x double dot, which is change in velocity with respect to time, mx double dot plus kx. Here also maa plus kx. So both are giving you the same result. So we can either solve using a Newtonian approach or a Lagrangian approach. So both will provide you the same answer. And for the higher DOFs in our syllabus, we are going for this Lagrangian approach for solving our problems. So this is the important derivative which you will be asked in your final end semester examinations. So I will give you an overall idea how we are solving this. So this is the equation of motion we have to solve. So this is the robot that will be provided, and we have to derive the equation of motion for a 2 DOF system. So it is a 2 DOF system. So you have a robot L1. This is the mass. This is a concentrated mass at the end, and this is M2. This is M1 and M2. So the length of link is L1, and the length of the second one is L2. Theta 1, theta 2 are your joint angles, and we have to find out the torque that are being generated. So based on this torque values only, we have to select a suitable actuator that can fit over here. T1 என்ன கிடைக்குதோ அதை விட அதிகமான மோட்டார் தான் ஃபர்ஸ்ட் நம்ம இங்கே வைக்கணும். அதே மாதிரி T2 கிடைக்கும், சூட்டபிள் டார்க் தட் இஸ் பீயிங் ஜென்ரேட்டட் பை திஸ் லிங்க் எவ்வளோ கிடைக்குதோ அதை அப்போஸ் பண்ணுற மாதிரியான ஆக்சுவேட்டர் தான் யூ ஹேவ் டு பிளேஸ் இட் ஓவர் ஹியர். So this is the key concept you are going to solve when using this equation of motion. So I will give you a general overview. So based on that, you can study this on the as per the Google Classroom sheet. So now consider okay. So finally we'll get T1, T2. I will give you an overall view. T1 கிடைக்கும், T2 கிடைக்கும். So you take this relation. So we are going to solve for using the Lagrangian approach. So L is equal to K minus P. So that is the formula that we have. L is equal to K minus P, where K is your kinetic energy, P is your potential energy. So we have to solve for the kinetic energy of link 1. Link 1 oda kinetic energy solve பண்ணனும். அப்புறம் potential energy of link 1 also we have to solve, and kinetic energy of link 2 and potential energy link 2 also we have to solve. So K is given by half mv square. Half mv square. And we will start with the term x and y. Start with the x and y, where x is equal to, using the forward kinematics, we will get L1 S1 plus L2 S12, where S12 is equal to sine of theta 1 plus theta 2. So a shorter version of this is S12. And y is minus L1 C1 minus L2 C12. This is solved using the forward kinematics. Since the robot is on the downside, we are getting this relation. இந்த ரோபோட் வந்து மேலே பார்த்த மாதிரி இருந்ததுன்னா, suppose if it is above ground, it is wall hanging, but this is the base fixed. So இந்த மாதிரி இருந்ததுன்னா, it is L1 C1 plus L2 C1 2. So this is x and y. Next we take the differentiation x dot and y dot. So we differentiate these two components and we substitute over here. So v is equal to x dot square plus y dot square, half mv square. So அதுக்கு பதிலா x dot square plus y dot square. We have to consider both the velocities. So v is provided by x dot square. X dot square na inga கிடைக்கிற value. So we have to square x dot square plus y dot square. So from that we will get v square. So we substitute this in the kinetic energy term. So kinetic energy half m. So we have to substitute everything over here, k1 and k2. So we get the kinetic energy term, and potential energy is mgh. So potential energy is mgh. So for h we have to take it the h inga பார்த்தோம்னா, this y term is the h here. So y term is the h here. So first link க்கு பார்த்தோம்னா இதுதான் வந்து y term, இது y term h, அது வந்து L1 C1. L1 C1 h க்கு பதிலா you have to substitute L1 C1. அதே மாதிரி potential energy for link 2, you have to, instead of h you have to substitute this one, this y term you have to substitute. So that will give you the final potential energy. So using the Lagrangian relation L is equal to k minus p, we will be substituting the kinetic energy term here and minus potential energy. Next, using the common formula that I told you, t is equal to d by dt of dou L by dou theta dot minus dou L by dou theta. So we have to use the same thing, dou L by dou theta dot, and then time derivative of this will provide you value, and dou L by dou theta. So final everything we have to use that d by dt of dou L by dou theta minus dou L by dou theta. So that will give you the torque required. It is a torque that is being calculated considering all the terms. So when you look at here, T1 is the torque required for the link 1. இதில் பார்த்தீங்க அப்படின்னா, it will include m1 m2. It will consider the mass of link 1, the concentrated mass at the end, link 1 and link 2. அதுவும் கன்சிடர் பண்ணிக்கணும். L1 consider பண்ணணும், which is link length of அதே மாதிரி m2 and L2 consider பண்ணணும். We have to consider link 2 ஓட length and mass. Also we have to consider the acceleration theta 1 double dot and also theta 2 double dot. So first motor select பண்றதுக்கு we have to consider m1 m2 L1 L2 theta 1 double dot, that is joined to one acceleration, theta 2 double dot joined to acceleration also we have to consider, and very importantly theta 1 dot and theta 2 dot. இதோட மீனிங் என்ன அப்படின்னா, which is your Coriolis component. Can anyone tell me what is where you find the Coriolis component? Since all from the mechanical, Coriolis component எங்க கேள்விப்பட்டிருக்கீங்க? யாராவது கேள்விப்பட்டிருக்கீங்களா Coriolis component?
சார் லிங்க் ரொட்டேட் ஆகும்போது இது
ஒரு லிங்க் ரொட்டேட் ஆகிறப்போ இன்னொரு லிங்க்கும் ரொட்டேட் ஆகும். ஸோ த ரொட்டேஷன் ஆஃப் ஒன் லிங்க், ரெண்டு லிங்க்கும் அட் அ டைம்ல மூவ் ஆகிறப்போ யூ வில் கெட் திஸ் கோரியாலிஸ் காம்பனண்ட். அண்ட் இன் அவர் multi-body system like robotic arm, since we are considering only for a 2D OF, the velocity of link 2, so link 2 oda movement to link 1 oda movement to will have a relative motion, and that is where this Coriolis component will come into picture, and we have to consider that also. And the gravity terms, also the gravity terms. So these are all the things that has to be considered for T1. Similarly, solving the same thing we will get for T2. So finally we derived this relation T1 T2, where T1 is the torque needed or the torque generated for this two link robot with the concentrated mass at the end. So which will tell you, so this is your inertial matrix, which is your inertial matrix, theta 1 double dot and theta 2 double dot. So this first term is your inertial matrix, joint inertial matrix also you can tell. So based on the robot configuration, suppose the folded robot will have fewer inertia, and the unfolded or stretched robot arm will have more inertia, and based on those things everything will vary. And also theta 1 dot and theta 2 dot, which is your velocity components, and also this Coriolis component also will come into play. This is your centrifugal component, and this is your Coriolis component, where theta 1 dot, theta 2 dot, so both are combined, and you have this Coriolis component. And final one is your gravity terms, irrespective of the angles. We have this in irrespective of the velocity terms, we have this gravity term. So the torque relation, we have to derive the equation of motion. First thing is we have to derive the equation of motion. So equation of motion has to be derived, and from there we will get the torque. So torqueல என்னென்ன காம்பனன்ட்ஸ்லாம் இருக்குன்னு பார்த்தீங்கன்னா, you have this inertial component, centrifugal component, Coriolis component, and also gravity components. So all these components has to be considered, and based on this we will get some torque. And the actuator selection for a robot arm should be based on the opposing. இங்க டார்க் வந்து நம்மளுக்கு ஒரு 10 நியூட்டன் மீட்டர் கிடைக்குது அப்படின்னா, இங்க எல்லாத்தையும் கன்சிடர் பண்ணணும். சப்போஸ் யூ சப்ஸ்டியூட் சம் வேல்யூஸ் ஓவர் ஹியர், சம் ரேண்டம் வேல்யூஸ் யூ சப்ஸ்டியூட் ஓவர் ஹியர் ஃபார் M1 M2. இதுல வந்து பாத்தீங்கன்னா கான்சென்ட்ரேட்டட் மாஸ் அட் தி எண்டுன்னு தான் கொடுத்துருக்காங்க. பட் ஈச் அண்ட் எவ்ரி லிங்க் ஆல்சோ வில் ஹாவ் இட்ஸ் ஓன் மாஸ். அதுவும் நம்ம வேற சினாரியோஸ்ல we will take all those things into consideration. So இது எல்லாமே சேர்ந்து you substitute some values L1 L2 M1 M2 theta 1 you substitute some values. If you get from here, it is 10 and 20 or 10 and 5 அப்படின்னு உனக்கு ஒரு வேல்யூ கிடைச்சது அப்படின்னா, ஃபார் எக்ஸாம்பிள் 10 and 5 அப்படின்னு T1 T2 10 and 5 அப்படின்னு கிடைச்சதுன்னா, what does it meaning, what is that implies is 10 நியூட்டன் மீட்டருக்கு மேல நீ வந்து டார்க் இருக்கிற மாதிரி மோட்டார் செலக்ட் பண்ணும். ஃபார் த ஜாயிண்ட் 1, the motor, the servo motor that you are going to select should be this. நீ வந்து ஒரு 11 நியூட்டன் மீட்டராவது நீ எடுக்கும். செகண்ட் லிங்க்குக்கு நீ எவ்வளோ எடுக்கலாம்? சப்போஸ் ஒரு 5.5 to 6. So the actuator selection, you have to solve this dynamic equations, which is your equation of motion. ஸோ டைனமிக் ஈக்குவேஷன்ஸ் கண்டுபிடிச்சாதான் ஒரு ரோபோட்டில் எந்த ஆக்சுவேட்டர் செலக்ட் பண்ணால் திஸ் டார்க் ஓவர் கம் ஆகும் அப்படிங்கிறதெல்லாம் நம்மளுக்கு தெரியும். ஸோ உங்களுக்கு வந்து இந்த டெரிவேஷன் கண்டிப்பாக எக்ஸாமில் வரும். ஸோ யூ கேன் லுக் அட் தட் கூகுள் கிளாஸ் ரூம் பிபிடி ஃபைல். ஸோ திஸ் இஸ் த இம்பார்ட்டன்ட் ஆஸ்பெக்ட் ஆஃப் த டைனமிக்ஸ். ஸோ இப்போ நம்ம முன்னாடி பார்த்த இது வந்து பார்த்தீங்கன்னா ஈக்குவேஷன் ஆஃப் மோஷன் ஃபார் அ 2D OF தான், வித் கான்சன்ட்ரேட்டட் மாஸ் அட் தி எண்ட். Concentrated mass at the end. It is only for a 2D OF robot in a planar. So planar la paakarapo we have only X and Y components. There are also scenarios where you have a 2D OF robot with the center of mass for the each link is at the center of the link. So இப்போ scenarios மாறும். ஸோ முன்னாடி வந்து கான்சன்ட்ரேட்டட் மாஸ் அட் தி எண்டுன்னு இருக்கும். இப்போ வந்து கான்சன்ட்ரேட்டட் the center of mass of each link is at the center of the link. ஸோ இப்போ உனக்கு வந்து center of mass வந்து மாறுது. ஸோ center of mass is getting changed and you have to derive the relation. ஸோ மோஸ்ட்லி எக்ஸாம்ஸில் டஃபாக கேட்க மாட்டாங்க. ஸோ கேட்குற மாதிரி இருந்தாலும் தே கோ ஃபார் திஸ் பேசிக் கான்சன்ட்ரேட்டட் மாஸ் அட் தி எண்டு. So for these kind of scenarios, we have to solve the same thing, and from there also we will get this T1 and T2. The final end we will get T1 and T2. Everything is only for a 2D OF robot, planar robot. But for the 6D OF robot, we have to solve for the tray. So this is the generalized equation terms for the. This is a TA, which is a generalized equation for a 6D OF robot. And finally, we will get this T1, T2, T3, T4, T5, and T6. So exams in the அளவுக்குல கேட்க மாட்டாங்க. They will stick with only 2D OF. So இங்க பாத்தீங்க அப்படின்னா 6th DOF robotல T1ல பாத்தீங்கன்னா we have to solve for the theta1 dot of theta1 double dot. So இதுவும் கண்டுபிடிக்கணும். theta2 double dot ஓட acceleration, theta2 ஓட acceleration, theta3 ஓட acceleration, 4 and 5 ஓட acceleration எல்லாமே கண்டுபிடிக்கணும். அதுக்கு அடுத்தது பார்த்தீங்க அப்படின்னா இந்த இண்டிவிஜுவல் centrifugal components, the velocity components also you have to consider. அதுக்கப்புறம் முக்கியமாக என்ன கண்டுபிடிக்கணும்? Coriolis component, theta1 dot, theta2 dot, theta1 dot, theta3 dot, theta1 dot, theta4, theta1, theta5. So Coriolis component of Coriolis component also we have to consider. அதுக்கப்புறம் gravity terms. So that will be brought over here. இங்க பார்த்தீங்கன்னா இதுவும் கண்டுபிடிக்கணும். அப்புறம் theta2, theta3. So all Coriolis component also we have to consider, and based on that only the torque will be calculated, and your selection of actuator should be based on the torques that are the opposing torque. So that is the key things. So this is just for your